Good day, calculus students. This lesson is on the hyperbolic trig functions and their derivatives. The first 2 pages will be reviewing or introducing what hyperbolic trig functions are, and then by page 3 we'll talk about how to differentiate those functions. Now the hyperbolic trig functions are defined as follows. Graph the first 2 on one grid and the third on the other grid. We begin with a function known as the hyperbolic cosine. Its notation is cos for cosine and then an h to represent the hyperbolic cosine. Sometimes for short, we'd call this the cosh or the cosh function. Of course, like trig functions, hyperbolic trig functions have inputs, also called an argument of the hyperbolic trig function. And the definition of hyperbolic cosine is as follows. It's the average, which means 1/2 of two different functions that are exponential, e to the x and e to the negative x. So it's really not a trig function at all. It's a combination of exponential functions. But the reason we call them hyperbolic trig functions will become clearer as we continue through this lesson. Now we've been asked to graph this function. We'll use technology to help us with this process, but one thing I want to analyze ahead of time is this decaying exponential, e to the negative x. As x approaches infinity, e to the negative x will shrink to 0, meaning that the entire expression here will approach simply 1/2 of e to the x. This will be a right-sided asymptote. It will not be a linear asymptote, it'll be a curving asymptote. But it's also a graph we know how to make, e to the x cut in half. This is a graph of e to the x going through 0, 1, and 1e, but now we want to cut this in half. So our orange function will be this function, and this will serve as a right-sided asymptote for the hyperbolic cosine. Now before I reach for technology, let me define what the hyperbolic sine is. Again, sin for sine and the h for hyperbolic. Sometimes we call this the sinh function of x. It is very similar. It'll be 1/2 of, but then the difference of these same two exponential functions. And once again, this portion of it, as x goes to infinity, will shrink to 0, meaning the function itself will also approach 1/2 e to the x as x goes to infinity. So this exponential function will also be a right-sided asymptote for the hyperbolic sine. Now reaching for technology, we have graphed the asymptote. I've made it orange and dashed. I reveal the hyperbolic cosine graph here in green and the hyperbolic sine graph here in blue. As you can see, both graphs, as we go to the right, approach that orange asymptotic exponential curve. So in our notes, we have hyperbolic cosine in green and hyperbolic sine in blue. Now the hyperbolic cosine looks very much like a parabola. It does form a cup shape, but it doesn't have the same reflective properties as a parabola. In fact, the shape, which looks like a parabola, is actually called a catenary curve. It is often used to model the shape made by ropes or chains when hanging from two fixed points, and is said to model the St. Louis Arch. Now, these two hyperbolic trig functions form the basis for creating the other 4 hyperbolic trig functions. So next, hyperbolic tangent. Just like with regular or circular trig, tangent is sine divided by cosine. Hyperbolic tangent can be found by dividing hyperbolic sine and hyperbolic cosine, which in exponential form looks like this, and then the 1/2s can cancel. As x goes to infinity, both of these portions will shrink to 0, so our overall function approaches e to the x over e to the x, which is just 1. So we know the limit as x goes to infinity of hyperbolic tangent is 1. As x goes to negative infinity, these exponentials shrink to 0, so hyperbolic tangent approaches negative e to the negative x over positive e to the negative x, which simplifies to negative 1. Let's use technology to graph this and confirm. Here's our graph of hyperbolic tangent. Notice as x goes to infinity, the outputs do approach 1, and as x goes to negative infinity, the outputs do approach negative 1. This function is used as a model for when one value transforms into another value, similar to the graph of arctangent, shown here in black, but the arctangent graph has asymptotes at pi halves and negative pi halves, which are slightly more inconvenient horizontal asymptotes. So sometimes instead of using an arctangent function to model phenomena of this nature, we can use a hyperbolic tangent function instead because its asymptotes are simple numbers. And here in our notes is the graph of the hyperbolic tangent. Okay, the remaining 3, hyperbolic secant is 1 over the hyperbolic cosine, which winds up being this function, which is the reciprocal of the hyperbolic cosine. Hyperbolic cosecant is the reciprocal of hyperbolic sine, which is this function in exponential form. And the hyperbolic cotangent can be found one of 2 ways. It's the hyperbolic cosine divided by the hyperbolic sine, or simply the reciprocal of hyperbolic tangent, which gives us this exponential expression. Their graphs are as follows in technology: hyperbolic secant, hyperbolic cosecant, and hyperbolic cotangent. you'll notice that none of the hyperbolic trig functions are periodic, unlike the regular circular trig functions. So already we can see some parallels between hyperbolic trig and regular trig, at least in how these 4 hyperbolic trig functions are created from these 2 hyperbolic trig functions. Okay, next page. Now, the hyperbolic trig functions are so named in part because they have identities similar to circular trig functions. Prove some of the hyperbolic trig identities below. So on this side of the table is a review of some of the key identities for regular circular trig that are useful in calculus. And then we compare them with some identities that are true for hyperbolic trig. And you'll see some astonishing similarities. With regular trig, cosine squared plus sine squared always equals 1. But with hyperbolic trig, it turns out that hyperbolic cosine squared minus hyperbolic sine squared will always equal 1, provided these arguments are the same. And then once this is true, you can easily establish these other 2 versions in the same way that these 2 Pythagorean identities can be easily proven, beginning with this one. Just take this identity and divide everything by hyperbolic cosine squared, and you'll wind up making this identity. Take that first identity and divide everything by hyperbolic sine squared, and you get this identity. So let's take a moment and just prove this one real fast. Let's do the hyperbolic cosine, square it, and then minus the hyperbolic sine squared. So replace each with their exponential forms and then square those. And when I square this product, I have to square the 1/2 and square this sum separately. So squaring the 1/2 gives me 1/4. And recall that when you square a plus b and FOIL, you get a squared plus 2ab plus b squared. So we're going to get e to the x squared plus 2 e to the x e to the negative x plus e to the negative x squared. Now over here, square the 1/2 gives 1/4, and then square this difference. Use the same formula, except we'll get a minus right here. Now all these powers here will multiply, and these powers will add, giving e to the 0, which is just 1. Keep in mind that e to the x times e to the negative x is the same thing as doing this, and we get e to the x over itself, which is just 1. So we get 1/4 e to the 2x plus 2 plus e to the negative 2x minus 1/4 e to the 2x minus 2 plus e to the negative 2x. And now we'll distribute. In particular, don't forget to distribute this negative as well. And then you're going to see a bunch of things cancel. These 2 terms will combine to be 0. These 2 terms will combine to be 0. And so we just get 1/2 plus 1/2. Sure enough, we get 1. So in the end, hyperbolic cosine squared minus hyperbolic sine squared will always simplify to 1. I won't take the time to prove either of these, but notice how similar they are to the regular trig, with one key distinction. For sine of an angle plus or minus a second angle, we have sine x cosine y plus cosine x sine y, but this sign right here will always match this sign right here. For hyperbolic sine, it's the same thing, except all the trig functions are hyperbolic trig functions, and whatever sign you see here is also what sign you see here. Now for the cosine of a sum or difference of angles, we get cosine of the first times cosine of the second, and then here we have sine of the first, sine of the second, but the sign needed here is always the opposite of the sign you need here, which is why the minus is above the plus. Now for hyperbolic cosine, the identity is the same, except the sign here will match the sign here. So this set of identities almost perfectly mirrors this set of identities. And then our double angle identities, sine of double an angle is 2 sine cosine. That's also true for hyperbolic trig. And cosine of double an angle is cosine squared minus sine squared. Over here we have virtually the same identity, except it's the sum. So be mindful that for regular trig, cosine squared plus sine squared simplifies to 1, but for hyperbolic trig, cosine squared plus sine squared simplifies to hyperbolic cosine of double the angle. Let's take a moment and just prove this statement. Recall hyperbolic sine is 1/2 e to the x minus e to the negative x. If I change this to 2x, then I change both of these x's to 2x. So hyperbolic sine of 2x is equal to 1/2 of e to the 2x minus e to the negative 2x. So 2 times hyperbolic sine times hyperbolic cosine looks like this in exponential form. The 2 times a half times another 1/2 just becomes a half again. And now I need to FOIL these 2. And they're conjugates of each other, so they should just produce a difference of squares, which we'll confirm. E to the x times e to the x is e to the 2x. Add the powers. E to the x times e to the negative x equals e to the 0. Add the powers, which is just 1. Negative e to the negative x times positive e to the x will become minus 1. And negative e to the negative x times positive e to the negative x, add the powers, we get negative e to the negative 2x. Now you can see that the 2 middle terms do cancel, and we wind up with a function that matches this function. Okay, there are many more hyperbolic trig identities, but these are the only ones we'll touch up upon. just to show you the similarities between hyperbolic trig and regular circular trig. Okay, the next page. Now we're going to talk calculus with these functions. Use the graph of each function to predict the graph of its derivative. In the first case, we have hyperbolic sine. Imagine a point on this curve and what the tangent line would be. I expect a positive high-value slope. And as we move along the curve, imagining the tangent lines, their slopes are getting smaller but still positive. And right here seems to be the least steep portion of the curve, because after that, it appears that the tangent lines get steeper and steeper and positive again. Here's using technology to show more explicitly what I've been imagining. Here we have a point down here in the third quadrant. The slope of the tangent line I've calculated is 6.13. As we increase, that slope drops because the tangent lines are becoming less steep. And then right here at the origin, this is where the slope is lowest. And we do have a slope of 1. And then the slopes continue to increase from then on, getting steeper and steeper again. So in our notes, when x is 0, we expect an output of the derivative to be 1. And then as we look at this portion of the curve, the slopes just keep increasing from 1. So I expect my derivative outputs to go up. And for this portion of the curve, working backwards, I expect my outputs to also just go up. With technology, when x is -2, the slope of the tangent line is 3.76 approximately. So the derivative, when x is -2, should have an output that's 3.76 approximately, putting it right here. When x is -1, the slope of the tangent line is now decreased to 1.54, lowering this point to 1.54. When x is 0, the slope of the tangent line is 1, so I expect the derivative to have an output of 1. And then as we increase, at any point that I stop, the output of the orange function should match the slope of the tangent line to the black function. And here it is played through. Slopes of the tangent lines of the black function become y-coordinates of the orange function. So I expect my derivative graph to look like that orange graph, which looks a lot like the hyperbolic cosine. Now back in our notes, looking at hyperbolic cosine, at this flat spot, the tangent line I'm imagining is clearly horizontal, so it has a slope of 0, so I expect the derivative to have an output of 0 there. At this point here, the slope would be very large but negative, and then the tangent lines become less and less negative until they get to a tangent line of 0, and then the tangent lines get more and more and more positive. So I expect my derivative to have large negative outputs getting closer to 0, and then from there to have large positive outputs. Using technology, we can see large negative slopes becoming a slope of 0, and then becoming larger and larger positive slopes. Plotting those slopes as y-coordinates, pausing at -2, the slope of the tangent line was -3.63 approximately, so we expect our derivative graph to have an output of -3.63 approximately. Here at -1, the slope of the tangent line should match the output of the orange graph. At 0, the slope of the tangent line matches the output of the orange graph. At 1, the slope of the tangent line matches the output of the orange graph, etc. So the orange graph represents the graph of the derivative of the black graph. Looking at these two results, it appears the derivative of hyperbolic sine will simply be hyperbolic cosine, and the derivative of hyperbolic cosine will be the hyperbolic sine. Let's confirm this. And we're going to compare by using the exponential definitions of hyperbolic trig to find these derivatives. So the hyperbolic sine is 1/2 of e to the x minus e to the negative x, and this is what I want to differentiate. Well, the 1/2 will stay, and I just have to differentiate now this function, which is a difference. So I just differentiate these two functions separately, term by term. Just recall that the derivative of e to the x with respect to x is just e to the x, but the derivative of e to a function, u, using the chain rule, will be u prime e to that same function u. This was discussed in a previous lesson. So when I differentiate e to the x with respect to x, I just get e to the x still, and then we have minus, and now I want to differentiate e to the negative x using the chain rule. So I'll get itself times the derivative of this exponent, and the derivative of negative x is just -1. I could put that -1 right there. So in the end, because of that chain rule, we wind up getting the exact same function, but addition between these two terms. Well, this is the exact definition of hyperbolic cosine. So it is true that the derivative of hyperbolic sine is just hyperbolic cosine. Well, that's also true for regular trig. Derivative of sine is cosine. So yet another parallel with regular trig. And for hyperbolic cosine, here it is in exponential form. Let's differentiate it. Again, the 1/2 will stay. We differentiate e to the x, which is itself, and then plus we differentiate e to the negative x, which will be itself, times a -1, which you can write before or after that term. but the effect of that -1 will simply turn this sum into subtraction instead. And this is the exact definition of hyperbolic sine. So the derivative of hyperbolic cosine is simply hyperbolic sine. This doesn't perfectly mirror regular trig, because with regular trig, the derivative of cosine of x is negative sine of x with a negative coefficient. And this is exactly as we predicted. Here is the graph of hyperbolic sine, and it made sense that the graph of its derivative would look like this, and it turns out it does because that is the graph of hyperbolic cosine. Same here. Here's the graph of hyperbolic cosine. It made sense that the graph of its derivative should look something like this, which it does because that is the graph of hyperbolic sine. Okay, let's go to the next page. Find the derivative of each hyperbolic trig function. So we have 4 more. To find these derivatives, we're going to express these 4 hyperbolic trig functions in terms of hyperbolic sine and cosine, and then use quotient rules as appropriate, and then some hyperbolic trig identities. For example, this first case, hyperbolic tangent is the same thing as hyperbolic sine over hyperbolic cosine. Differentiate this using the quotient rule. So we know we'll get a u prime v minus uv prime over v squared. So the derivative of hyperbolic sine is hyperbolic cosine. So there's my u prime, but then times v, and v is the same thing. So I can just say hyperbolic cosine squared, and then minus u, which is hyperbolic sine, and then times the derivative of v. But the derivative of hyperbolic cosine is hyperbolic sine. So I can just put a square on this hyperbolic sine. And then all over the square of v, which will be hyperbolic cosine squared of x. Now the hyperbolic trig identity gives that this numerator will just be equal to 1. That was this identity right here. So we get 1 over hyperbolic cosine squared. And since 1 over hyperbolic cosine is the same thing as hyperbolic secant, we can write this as simply hyperbolic secant squared of x. Okay, hyperbolic cosecant next. That's the same thing as the reciprocal of hyperbolic sine. Differentiate that, again, using the quotient rule. We have a u and a v. So the derivative of the numerator is 0, so that just goes away. So times v, which I don't need to write because times 0 will be 0, minus the numerator, which is 1, which I don't need to write, times the derivative of v, which is hyperbolic cosine. And then all over the square of v, so hyperbolic sine squared of x. So this will be negative, and I can factor that denominator into 2 different hyperbolic sines and split it up, such as this. Well, this expression is hyperbolic cosecant, and this expression is hyperbolic cotangent. So in the end, my derivative is negative hyperbolic cosecant, which I'll write first, and then times hyperbolic cotangent. Okay? Hyperbolic secant next. This is the reciprocal of hyperbolic cosine. And differentiate that, again, using the quotient rule. U prime is 0, so u prime v will just be 0, minus u is just 1, and derivative of v is hyperbolic sine, and then all over the square of the denominator. Similarly, if I factor that denominator and split this up, I can see that we have a hyperbolic secant here and a hyperbolic tangent here with that negative coefficient. So we have negative hyperbolic secant, which I'll write first, times hyperbolic tangent. And then finally, the last of the hyperbolic trig functions, hyperbolic cotangent, is hyperbolic cosine divided by hyperbolic sine. This is what we'll differentiate, again, using the quotient rule. The derivative of u is hyperbolic sine, but then times v, which is also hyperbolic sine, so I'll put a square there, minus u times the derivative of v. But the derivative of v is hyperbolic cosine, so I can just put a square there, and then all over the square of the denominator. Now this difference is backwards of this difference, but it's this difference up here that's equal to 1 using the hyperbolic trig identity. So down here, I'm going to have to factor a negative sign out. And recall that if you have a difference and you factor a negative out, you can just reverse the order of the difference. So that allows me to write hyperbolic cosine first, and then minus hyperbolic sine squared second. And now I have the difference in the correct order, whereby we can replace what's in orange there with a 1. So we get a negative 1 over hyperbolic sine squared, which is the same thing as negative hyperbolic cosecant squared of x. Okay, you may have already noticed all the parallels between hyperbolic trig and regular trig. Let's go ahead and summarize in this table real fast. So the derivatives of the regular trig functions. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of cosecant is negative cosecant cotangent. Derivative of secant is secant tangent. And derivative of cotangent is negative cosecant squared. These derivatives were all done in a prior lesson. And what we just discovered is that the hyperbolic trig functions, which are really exponential functions, not trig functions, have such similar parallels. The derivative of hyperbolic sine is hyperbolic cosine. The derivative of hyperbolic cosine is hyperbolic sine, no negative. The derivative of hyperbolic tangent is hyperbolic secant squared, which we just did right there. And then our other three, hyperbolic cosecant differentiates to negative hyperbolic cosecant times hyperbolic cotangent. Hyperbolic secant becomes negative hyperbolic secant hyperbolic tangent. And hyperbolic cotangent becomes negative hyperbolic cosecant squared of x. So the parallels between the two are obvious. The only difference is where the negative signs are. In the case of regular trig, if your regular trig starts with a c, such as these three, then there is a negative in its derivative formula. But for hyperbolic trig, it's these bottom three hyperbolic trig functions that produce the negative in the derivative formula. Other than that, the parallels are 100% aligned, which makes them easy to remember. Okay, one more page. This page explores the effect of the chain rule when you have hyperbolic trig of a function other than simply the independent variable. So find two functions f and g such that y is their composition, y being this function here. Then find the derivative, dy dx. Well, the way we want to view the composition here is that the argument, we're going to call g of x. This is the function that's being composed, and it's being composed into the function f of x, which is this function, but using an x instead of the orange highlighted 4x minus 1. So simply cosh, or hyperbolic cosine, of x. And sure enough, if you take this function g and plug it into the function f where the x's are, you do in fact get the function y. So y is f of g. Okay, in that case, the derivative of y, using the chain rule, should be f prime of g and then times g prime. This was covered in a previous lesson, which means next I want to find the derivatives of f and g. Well, g prime is simply going to be 4, and f prime, the derivative of cosh, is sinh, or hyperbolic sine. So now, using this chain rule, I want to take g and compose it into f prime. So here's g, but this time it gets plugged into all the x's of f prime. So we're going to have hyperbolic sine of 4x minus 1. And now we multiply all of this by g prime, and g prime is simply 4 in this case. So in summary, to differentiate hyperbolic cosine of a function that's not just the independent variable, we differentiate hyperbolic cosine, which is hyperbolic sine, plug in that same function, but then multiply by the derivative of the argument. Commonly, that 4 will be written in the front, giving us this expression. That allows me to create a generalized hyperbolic trig rule for hyperbolic cosine, this case here. Notice u does not match the x here, so we assume u is an unspecified function of x. Could be anything, but we will get hyperbolic sine of that same argument, and then times the derivative of that argument. And the presence of this u prime is the chain rule. All of the formulas generalize in this way. The derivative of hyperbolic sine is hyperbolic cosine of the same argument, but then chain rule times u prime. The derivative of hyperbolic tangent is hyperbolic secant squared of the same argument times the derivative of that argument. The derivative of hyperbolic cotangent is negative hyperbolic cosecant squared of the same argument, and then times the u prime, which I'll put right after that negative sign. Derivative of hyperbolic cosecant is negative hyperbolic cosecant of the same argument times hyperbolic cotangent of the same argument, and then chain rule times that u prime. And finally, the derivative of hyperbolic secant is also negative hyperbolic secant of u times hyperbolic tangent of u, and chain rule times the u prime. These 6 generalized formulas are the ones that are most useful moving forward, but they're easy to remember because, again, they parallel the regular trig rules so closely. Okay, 4 examples, and we'll call this lesson done. All right, so find each derivative below. First of all, x is the independent variable, so here we have a function of x as the argument of hyperbolic sine. If you want, you can call that argument u. So we know that the answer to this should be u prime hyperbolic cosine of u. So we put the derivative of square root of x, which using a shortcut is just 1 over 2 square roots of x. Now I'll put that in the front, and then times hyperbolic cosine of u, and u is also just square root of x. Notice you can sometimes not necessarily write these parentheses every time around the argument when it's obvious what the argument is. Next example, w is the independent variable. Here's a function of w as an argument of hyperbolic tangent. We can think of that as a u function. This 3 will stay because it's a coefficient of a function. So I know I should get 3 u prime and then hyperbolic secant squared of u. So we get 3. Now we put the derivative of u, well, e to the w, where w is the independent variable. That derivative is just e to the w. And then times hyperbolic secant of u, and u again is e to the w. If this starts to look confusing to you, then sometimes it's nice to put the argument in its own parentheses. Okay, next example. Z is the independent variable. I have a 2 over z plus a 1 as the argument. So here's a function of z. This is my u. And I'm going to rewrite it. It's really 2 times z to the minus 1 and then plus 1. That'll help me with the power rule when I have to find u prime. So our basic form, we have a negative that leads us off, but then we have a derivative that's again going to be negative, u prime, hyperbolic cosecant of u times hyperbolic cotangent of u. So these negatives will cancel. So we have a positive u prime. Use the power rule on this part, so we get negative 2z to the minus 2. And then, of course, the plus 1 will differentiate to 0. So there's my u prime times hyperbolic cosecant of u, and u is 2 over z plus 1, times hyperbolic cotangent of u, and u is 2 over z plus 1. And here is our result. In the last case, we have v is the independent variable this time. So we have a function of v sitting here. I'll think of that as my u. And the derivative of hyperbolic secant is negative u prime hyperbolic secant of u, hyperbolic tangent of u. So we get a negative of u prime. U prime is going to be found using the power rule. 9 times 5 is 45, and then v to the 8th. Here's my negative u prime, and then hyperbolic secant of u times hyperbolic tangent of u. All right, this concludes our lesson on the hyperbolic trig functions and their derivatives.